and the current state-of-the-art capabilities of modern winders. Tom has been closely involved with the specification and application of safety-related rebuilds to several North American pulp and paper producers. Lee Salda has been involved with controls and automation of finishing equipment for over 30 years, starting with hardware and software design and eventually leading to management of a team of design engineers. Most recently, Lee has concentrated on improving product safety by targeted rebuilds of existing finishing equipment, including multiple winder upgrades. I'll now hand it over to our presenters, Tom and Lee.
Hey, good morning to all, and thanks for taking the time today to review the subject of improving winder safety. Today's discussion is going to be mainly geared for improving safety on existing winders through winder rebuilds, but we're going to keep a pretty keen awareness of the safety requirements and standards for new winders. So why the emphasis on winder safety? Well, basically the main focus typically in a paper mill is on the paper machine, but when it comes to safety, it's no secret that the operators on the winder are exposed to a fair amount of hazards. And essentially a winder is a batch process, so depending on the paper grade, basically every 6 to 12 minutes we've got another set coming off that winder, and obviously there's considerable risks and hazards around that set change. One of the new things to be aware of in the last couple of years has been more or less the acceptance and implementation of the EN or ISO 13849 machinery standards, and those essentially are now in place. And it's a standard that it's just not a European standard, but it's being utilized here in the States as well as Canada. So that's something we've always got to be aware of when we're looking at altering the safety practices on our equipment, especially winders. Another item in terms of paper mills, paper corporations, there's been a really intensified view of safety and how it applies to our equipment, and many paper mill or paper corporations have implemented their own standard, current standards for winders in their organization. As far as increasing the focus on safety for guarding, if you look at basically anything in our daily lives, whether it's automobiles or tools we use or just things in our home, there's been an overall major increase in safety awareness in all our products. And so that basically comes to us via a number of changes in regulations and laws. Our industry itself, we just touched on it, has really intensified our view on safety. And in terms of paper machinery, with the increase in productions and higher speeds from years past, those relate to basically some more serious injuries, so we keep that in mind. And with the advances in technology of new equipment, it only makes perfect sense to apply that new technology when retrofitting existing winders. So that's a big part of what we do and a lot of what we'll discuss today. And of course, any lawsuit or litigation against corporations because of injury is, should always be avoided wherever possible. Okay, so if you think about, and this discussion is essentially geared toward folks in your mill. If you can kind of envision the winders in your mill and start to think about the obstacles or difficulties of improving safety on your winders. And this photo here is a shot from a winder basically in the 1950s. And if you still have any of these winders in your mill, it's a major undertaking to get that retrofitted. But back in those days, as you can see, there wasn't a whole lot of design thought on safety. You've got a lot of open nips, you've got open drive shafts, maybe open gears, very little guarding. So hopefully most of these type of winders have been replaced and you're not having to deal. If you are still having to, well, that's many cases looking at a new winder. But if we think about in the 60s and 70s with the overall growth of the paper industry, and machines got considerably wider. They got faster. A lot more steel and beefiness to winders was obviously applied. But as you can see from this shot, there is really no advancement in safety guarding, and basically the controls were all relay based. And as you can probably envision, there's still a number of these winders out there, probably looking a lot like it was when it was installed, 30 to 40 years ago. So these type of winders are a big part of the safety improvement in winders today. And then if we shift to the 80s, there was a lot of new production that came online, and machines got considerably wider again. The implementation of PLCs for control in winders was a pretty big advancement, and that helped, rather than just mechanical guarding, via controls, started to see some improvements in overall winder safety, as well as additional barriers and guarding that you can see here. And then, of course, today, if we're looking at a new winder today, all of the current standards, the EN standards we mentioned earlier, would apply. And really, the winders today are basically our measuring stick for how we take some of these existing winders to that level of safety, both in guarding, fencing, access control, all the above. All right, so if you think about winders in your mill, the big question is, where do we start? You've got a lot of things to think about, but you've got to actually begin the process. And how we typically go about doing that is, first item is to perform a risk assessment, which whether it's done via winder vendors or whether mills will do that on themselves, or some corporations will go have a team that will go to their other locations and come up with those list of hazards. But basically, we're identifying the hazards themselves and the actual severity. And then the point there is to try to prioritize what are the most important things to address. And this second point is basically you've got to develop a scope for this safety improvement, which is obviously the more safety changes or upgrades you perform, those costs go up. And so there's always obviously a limit to the amount of money that can be applied. So the question is, how safe is safe enough? And we can look at that via the Category 1 or Category 3 levels or the PL levels, and I know Lee will be talking about that in more detail in just a bit. But those corporations that have already developed their safety standards, and a lot of those have already been referencing the EN 13849, and so if you work for a corporation that has already done that, that's an excellent tool to begin the process, and you've got a kind of a leg up in terms of what your scope's going to end up being. All right, so the next question, and as far as the safety upgrade and what that all does, obviously it's going to allow the operator to work safer and minimize risk. But a big factor that we've seen in recent years is by limiting access, there typically, at least initially, is kind of a reduction in actual throughput on the winder. So you need to plan that as part of, at least look at that as part of your upgrade, because that's a critical thing. You may overcome it, especially if the winder is got a fair amount of capacity to stay ahead of the paper machine. But if it's very tight now, chances are you're going to need to add some automatic functions to gain that capacity back. We'll touch on that more here in a little bit. So this balancing act of how much safety to be applied to each winder varies, of course. I just mentioned about the ability of the winder to still maintain production and allow hopefully advancements down the road to stay ahead of the paper machine. And all of that, of course, you're doing a balancing act with the available funds. So with that, I think, Lee, if you could give us an overview on some of these new safety guidelines.
Just a few words on the new understanding the new safety guidelines. The EN ISO 13849, it defines the general principles for design of control circuits. So it replaced the former EN 954 standard. And again, it's a European standard, but the EN standards have three basic classes. The A class is a basic general guidelines. The B, which in this case is 13849, provides safety requirements and guidance on the principles for the design and integration of safety-related parts of the control system. And the C class is the equipment specific, and for winders, it's the 1034-3 specification. And when we do winder improvements, as Tom alluded to, how much do you do? Here are different steps you can take. Generally, the first starts at the bottom. All of these aren't necessary. They're all probably necessary to reach 13849, but which parts do you do? These are the topics that we're going to discuss today.
Okay, so typically your base area that gets looked at first and really addresses the bulk of these issues that you'll find during this risk assessment is the guarding, fencing, and the warning and the e-stop area. And what that really involves is essentially you're really limiting access to that winder. Currently, your operators probably, because they're experienced, they know where and when they need to, to make their move and go into certain spots on the winder. But what this in terms of following the standard plan for 13849, you can see the fencing starting at the unwind. With the retractable barrier there. Up until a couple of years ago, operators potentially could have the ability to walk into that unwind while you're running at top speed. Well, nowadays, that is an area that gets looked at to limit access there. Of course, the full fencing through the unwind stand, access into the slitter section. Typically, you'll see maybe a sliding gate on the tending side and maybe a hinge gate on the back side of the slitter section. The area between the slitter section where normally there's spreaders, your spreading after slitting is there, your ejector is there. We'll typically gate that off there as well, essentially enclosing that whole wind-up area. The core chuck assembly is raise and lower, and will prevent an operator from potentially getting underneath that. That's all guarded. And then, of course, the wind-up area is gated as well, and then, of course, the discharge. The wind-up and the discharge many times being probably the most potential for risks and hazards on the winder. When we apply the fencing and gates, we try to do it with a creation of safety zones. And rather than just putting a big fence, essentially people call it caging the winder, we do it such that we're able to control specific zones so that we can try to keep the uptime and capacity as high as we can. So in reference here, if you see an operator that has to go in the unwind zone between the unwind parent roll and the slitter section, that particular area will remove the hazards from the unwind zone, but that doesn't mean the operators in the discharge zone can still be in there and functioning and deal with taping tails and lowering the cradle down. So that's the thought process when we design fencing and gating around the winder. This example here is that retractable fence, and with that engage, we apply. There's logic obviously to every one of these zones, but an example that that retractable fence could be down, and the unwind could potentially run at a slower speed, or we can limit crane movement over that if that fence is down. It's just another form of interlocking the functions on that unwind. This view here shows a winder that was probably installed 12 or 15 years ago, and it gives you some of the main functions, as we just touched on: the fencing, the lockable gates, access gates, a number of sensors, light scanners in the discharge area, and a full-width E-stop in and around the front drum, which is a typical hazard spot for an operator. All right, the means of into and out of these zones is done via an interlocked gate. And this picture here shows a fortress latch, which is a very prevalent type of latch in today's winder area that we use quite a bit, but also trap keys. Some corporations have implemented the standard of utilizing trap keys, which means an operator to go into an area, it's basically one of the rules of operating is he removes that key to go in and take care of issues in and around the winder, front drum, and then when he comes back out, that key needs to be replaced before that zone can be reset. So that's one way some corporations are operating their access control. As far as the function and how these gates work, just an example, you see a access panel push button. You see two push buttons, and if an operator wants to enter into that area, he'll basically push the green button, which is the upper button, and it will either turn on in green, meaning everything is safe in that area to enter, or it'll flash saying there are still activities going on and you need to wait. So once it goes to full green, he can open that latch, which is interlocked. It will be allowed to be opened, and then he'll go ahead and take care of his functions and then come back out, and he'll have to reset that zone, which is the orange button below. And of course, placards, any safety upgrade is gonna list clearly via words as well as pictures all the hazards that are in that area, and it's just an additional reminder of all the residual hazards that are still, in fact, in this particular zone. Okay, this view here just shows basically the area in and around the front drum and the cradle, which the operator spends a lot of time, especially if he's still doing a lot of manual functions on the winder. The main things here to look at are that roll barrier, which raises and lowers up above. That's this yellow beam here. But that is, in addition to that, we've got this front drum pivoting splice cover, which also acts as a mechanical piece fixed barrier that the operator can lean on when he's in and around the cradle, whether he's tearing the tail or taping cores or what have you. Keeps him away from that front drum. Also, we note there's a full-width E-stop, so if he's splicing or jogging or threading and has any kind of issue with a nip or safety, all he has to do is step on this full-width red, it's like a rubberized E-stop switch, will kill power at that time. So, and then also we typically look at having a control panel right close by to where all the activities are, which is on the back side of that cradle, and they'll be able to control threading and splicing and jog functions and knife actuation. So that avoids the operator taking extra steps heading in and out back outside the frame to do that. An area on the discharge is which is obviously has a high potential for issue is these rolls that are still in the cradle, and we'll always have a light curtain and or scanners in that area, sensing if anybody personnel is still in the area prior to the cradle being lowered to the floor and rolls being discharged. So all the cradle functions are tied to these light curtains and light scanners, which the operator will have to, once they're broken, will have to reset and has line of sight to the cradle before he's able to take rolls to the floor. And with that, Lee, I think if you could expand on some of the control area there.
Yeah, another step in the winder safety improvement is to update the electrical controls. Some typical items that are updated is the PLC on the winder is replaced with a safety PLC. It will incorporate safety I/O. Another option is to remove power from the existing fluids and electrical circuits using safety relays. And really, normally this accompanies the safety fencing, gates, and zones. So when you put on fences, gates, you make the different zones, normally the electronics is also updated at this time. Another improvement in safety can be to use new fluid control systems. That basically replaces all the hydraulic and pneumatic valves. When we replace circuits, we will take them to the latest ISO 13849 level, and that will be determined from the risk assessment that you do on your winder. Do we need a Category 3, a PLC, a PLD, and we'll go into those shortly here, but we will take the fluids to the level determined by your risk assessment. Normally it means redundant valves for all serious or moderate hazards. We also add much circuit feedback devices to get monitoring so we know if our outputs are being controlled correctly. The early PLCs that were put on winders consisted of a PLC, but single inputs from gates, if you even had gates, single inputs from all the safety devices, including the e-stop buttons, one solenoid valve, for example, to control a hydraulic cylinder, and maybe a limit switch to tell you moved to where you wanted to move. That is basically an example of a Category 1 circuit. You have one input, one logic element, and one output. The different safety ratings that we will use on winders, they would start with a Category 1 circuit. And they will still be used today, but mainly on movements on the machine that do not cause a hazard. Perhaps turning on an air blow, or something that is rated a very low hazard. We can, the standards still allow a Category 1, or if 13849, a PL, which is performance level, PLC category, which can be done by using a Category 1 structure and using components that will have a mean time between dangerous failure of 30 years or greater. When the risks are, from the risk assessment, say we need a PLD, we will use a Category 3 structure. That is using redundant components, two inputs from safety devices, diagnostic coverages on the output, and redundant outputs. To reach PLD with a Category 3 structure, you simply need to use components that are rated to have a mean time between dangerous failure of 30 years or greater. This is the Category 3 structure. You'll have two inputs, so your gate locks, your e-stop push buttons, all the safety devices will have dual inputs. We will have two logic controllers that will monitor each other, and we will have two outputs with monitoring to ensure that the outputs are in the state that the PLC told it to go to. These three elements form up the ISO 13849 circuit. It's an input, the logic, and the output. and combined, these three have to have the mean time between dangerous failure of 30 years. And this is the new circuit compared to the circuit I showed before that we would have on a PLD rated circuit. So we'll generally have a safety PLC, dual contacts from safety devices, redundant actuators for movements. So in this case we're showing two solenoids that need to turn on to cause movement. The device will have extra monitoring on to tell if it is really moving or pressurized. And this is a typical circuit.
Okay, let's touch base a little bit about control changes and what the operator typically would see in his interface to the winder. This is a pretty typical picture around a winder. It's a control desk or a bench board, which has its share of hardwired push buttons and analog meters, and perhaps over the years it's been updated with a panel view or a drop-in type of interface device. But in most cases, when a new PLC is put in and we start looking at the additional I/O for all safety devices, many times we'll go to a complete new bench board where you're looking at a PC-based operating system. There'll be a couple basic hardwire buttons for e-stop and resets and things like that. But essentially the operator will start to deal with the winder and interface via a PC system as well. And you notice in the corner there's a video board. A lot of mills will add cameras to get better viewing of spots where in the past may have been hard to see. So that's another area where mills are looking to implement improved visibility. Now with the advent of the new safety PLC and the additional interlocks required to monitor safety, a help or a diagnostic system is very, very important to kind of keep the uptime up and allow the operators to be able to troubleshoot typically on their own. And so this is just an example of a kind of a help screen that would be provided typically, which is monitoring all of the interlocks for that particular section on the winder. So if there's an issue and a function's requested or a button's pushed to basically begin a function and it does not happen, the operator can go in and either click on that particular function. As an example here, he was expecting the rider roll to come down on a new set of cores and it did not. So he can go into his help system and look at all the interlocks required for that function to take place. And the tool there where it says status, if it comes up red, that means that it'll tell you exactly why it's not functioning. And if the operator can go physically out in view to see the issue, most cases they can figure out the issue on their own. If by chance, if they can, obviously they avoid calling the E&I techs and resulting in downtime. But all the PLC addresses are there, the device names are there, and it's a very good tool for trying to improve overall runnability and uptime for the winder. Okay, mechanical holding devices, which is essentially a latched device for any mechanical item that is raising and lowering. And so the key here is that we're providing the ability for that assembly, which is obviously considerable weight or mass, to be held in a position, typically in an up position. When it's in a raised motion, we're not just relying on the power via hydraulics or pneumatics. We're going to mechanically hold it. So examples of that would be the cradle weight or intermediate position. The nip guard, of course, up and down. We would hold the nip guard in an up position, and then rider roll and core locks or core chucks. We would provide a full travel latch there to provide a mechanical means of holding throughout the travel. And then also some ejectors. Typically an overhead ejector, if we lost power, there would be some movement because the center of gravity would take it forward. we would also provide holding devices for that. So just to kind of run through some examples, in and around the cradle obviously can be a hazardous area, especially with a full load of rolls in the cradle, and typically the operator will take that down to some position where he'll tape tails while the rolls are still in the cradle. So that cradle, as we mentioned earlier, takes its interface with the light curtain or the scanner. If those conditions are right, they're able to take that down. So what we apply here is a set of stops in the lower portion. It's a pneumatic cylinder which is being monitored with proc switches either for engage or disengage. And that when the cradle would come down to the intermediate stop, those pins would extend, and they extend for the purpose that if we lose cylinder, we would break a cylinder, or the pressure line would break in the event. These pins would be there to catch that cradle. It would not allow those rolls to be discharged. So that it extends and retracts with every time the cradle comes in intermediate position to protect the operator while they're in front of that cradle. When it comes to core chucks and rider roll, this is an example here. As that set is building and the core chucks are obviously growing with the roll, they're raising, we constantly monitor and keep those chucks latched into a fixed position. And obviously when they retract and set change, the cylinder would retract and allow those chucks to go back down to the home position in the drum valley. But similar for a rider roll, we call many times called the dragon back, which is also providing that continuous latching on the raise and lower. Here you see it for the chucks, as well as this area here would be for the rider roll. Okay, threading improvements. So if you once again think about the winders in your mill and the efficiency of threading, and if you've got a system where your operators, if it's less than, say, 90% effective, where when they thread, the tail goes exactly where it needs to be, and if it's less than that, typically they're on their hands and knees trying to help the sheet, guiding it through the slitter section and or spreaders and under the drum, that allows the operator to be exposed to considerable risk. So if that's the case, threading improvements really need to be looked at, and typically, from the slitters to the rear drum, there's a number of areas that can be addressed there. We'll have a few examples here shortly. When you come to splicing is one of the more dangerous functions on a winder, both in and around the front drum, but also getting the tail up and around the partial set, avoiding operators crawling into the winder pocket with who knows what, broomsticks and all kinds of other things. I'm sure we've all seen that. We need to provide the proper assist for air jets. Web holders on the rear drum, keeping the tails or the individual webs from falling and getting into the pit, that's a concern. And then a couple areas in just actual change in operation and how they thread. Typically, recent times, we recommend that the winder get threaded without cores, and not putting cores in until actually the winder is actually threaded. And then also some functions in terms of hold to run. The winder, when you're making a splice, the operator will actually have to hold the push button to advance the drum at slow speed while that, rather than just letting it turn. And then also during threading, we would not rotate the front drum. That's just another change in process. Okay. Threading improvements, couple examples here, one a vertical slitter section, one a horizontal, either through powered nip assemblies via belt or rollers, as well as thread pans, allowing the sheet to be threaded effectively, efficiently through the slitter section, and then from there, advancing that tail through the slitter table rolls and then down and into the under drum threader. There's devices that can avoid the operator having to put himself in bad spots. So a couple examples of that. A lot of folks nowadays refer to hands-free Threading in and around the slitters, which obviously is a hazard, just sharp edges and keeping the operator's hands away from that. There's a number of air pans that would take the tail up and over a lead-in section, and air lubricated pans would guide it down in and around. This would be a guide roll up above here. You can see the pan coming down, guides the sheet around the first table roll. This air lubricated pan, which actually indexes in and out of the sheet, but during threading, obviously it slides down in, and that tail will come on and rest on it via air lubrication and take that through the slitters, which shortly thereafter it's caught by another belted nip assembly, which is nipping the tension roll here, and then taking that on through the dual spreaders or single spreaders, if you will, and then onto the drum assembly. Belted, this is that powered nip threading assembly, which would engage on the tension roll after slitters, and as you can see here, would take it through your spreaders and to the drum. Here again, avoiding the operator from having to actually crawl in and around there and put themselves in harm's way. Now, when it comes to splicing, we mentioned about the first concern is being able to thread that tail on a partial set, and this diagram gives you an idea of multiple diameters that you're going to try to get the tail up and around, and obviously the larger the diameter, the more difficult it is to get the tail. So a series of air blasts or splicing jets mounted on the center of the winder, typically on the back side of the slitter beam. First challenge is to peel that tail off of the rear drum after it comes up and around and get it blown onto, we use the term plaster it onto that partial set and keep it there. So as that tail keeps advancing, it doesn't want to flip back upstream, it wants to flip up and over the partial set. That's a critical element to keeping the operator out of a tough spot. Okay, relative to splicing, many mills are looking strongly at covering up that front drum during a splice. So there's a cover or a guard now, if you will, that pivots about the front drum, and this gives you an idea of a partial set in the pocket. You've got a full width pivoting cover that rotates about the front drum. You see a light curtain in this area, which is constantly monitoring that area, and if an operator would go in and break that light curtain, it would kill power to that movement of the guard or the cover. Okay, in normal operation, when an operator wants to advance this, it will pivot about the front drum until it actually we have a photo eye, which is the leading edge of that, and when the eye is broken by the partial roll, the assembly stops in a very tight spacing to the existing or the partial set. So we will provide a tape surface or a different feel so the operator, while he's looking at the roll, can tell that his hands are very close to that potential nip area. So that's a look at that. This diagram here just gives you an idea, on the size of the roll, whether it's a smaller 14-inch roll or a mid-size or even a 50-inch diameter roll. It will pivot till that light or photo eye is broken, and then you can see how the operator typically is leaning on that front drum and avoids this nip area. The nip area between the front drum and that partial set is typically the main hazard for making a splice, where in the past fingers and hands kind of can get caught into that area. Okay, finally, when we mentioned earlier about the ability for the winder to keep up. When you envision a gate and a fenced off area, all sections of the winder, and we have a very good potential for having a fallback and overall capacity. So we need to look strongly at what other features could be done, automatic functions, to both gain some of that capacity back, but also further reduce the operator's exposure to hazards. And one of the main things is set change. Set change is probably, here via capacity calculations, but normally that proves to be one of the biggest areas of improvement where you can gain capacity back. And those functions, if it's a manual winder, the core loading, the taping, the sheet cutoff, all that are typically anywhere from 2 to 3 minutes normally, but automatic set change will take that time down to 30 to 40 seconds typically. Another area of avoiding hazards is automatic wound roll tail end gluing. And what that does is it eliminates the operator's need to be in and around the front of the cradle taping tails. So we'll give it a couple shots that'll show how that function works. Of course, automatic slitter positioning avoids the operator in and around the slitter bands and blades on a regular basis. If you're making decal changes on your sheet and the operator has to go in and scallop out the sheet to be able to move his trim slitters, there's some assemblies called automatic trim ribbon cutters. That's another good tool. And then, of course, tail preparation and broke removal, where the operators in the past maybe are using a manual knife and they're slabbing down reels. That's another area where you can avoid a lot of those potential hazards and save time. So here again, the key point is to gain back some capacity or throughput, but also remove the operator from exposure to those hazards. Okay, just quick couple looks at the components that are normally involved in a set change. First, you've got to get the cores into this core loading device, which is typically part of your ejector. So a core table where the operators would manually load those on via gravity, or if it has to be powered depending on the configuration and where it's located. But essentially those cores end up on a core pusher, and those cores get pushed into the roll ejector, which has a core loading function. And while they get pushed, they're being sensed, the leading edge and the trailing edge, with a glue assembly. It's a hot melt glue system, and those glue nozzles are activated and will spray a glue stripe onto the core as it's being inserted into the core loader. The next basic function is an automatic sheet cutoff, which typically would pivot about the rear drum and is going to rely on the ejector with the set ejection to tear the tail or shear the web, if you will. And that's what typically cuts the tail. It makes a nice clear cut all the way across the rear drum and allows the set to then go on into the cradle. And then after that, you can envision this core loader, which is a separate assembly on an ejector, and via vacuum. Now keep in mind we have glue on this core, so you can't just drop cores into that drum valley for fear of getting glue on your drums. So those cores via vacuum need to be placed very accurately, and that's what this assembly is showing. You see the different motions of the ejector. The separate core loader assembly drops down and sets the cores, pre-glued cores, in proper position, and the ejector will then retract, and the rider roll core chucks come back down and get into position. And that's how you're able to get to a 30 to 40 second set change. Okay, the mention of tail end gluing, which is essentially applying a glue stripe to the tail, or to the web, I should say, in and around between the last spreader roll, after slitter spreader roll, and the rear drum. You can see, envision that would be a very tight spot. Typically is, and is typically located in and around the pit of the winder. And so how this operates is when the winder or the set is decelerating and getting very close to zero speed, we have a traversing glue assembly that'll go full width across the winder, and will spray a glue stripe on the web itself. And then as that stripe is, here again it's moving very slowly, that stripe will continue up and around the rear drum and actually go through the nip of the set being wound and get just above that, and that's where the winder will stop. Okay, and this obviously is tied very close to controls, and there's a lot of tuning to get that to function that way. But at that point, your set, your cutoff knife would come up and cut just behind that glue stripe, and your sets are then glued and ready to go to be discharged to the floor. Okay, one other last item to touch on in terms of avoiding some hazards in and around is if you can envision your current order sets and your customer base, and if you've got situations where sometimes your full width decal coming off your paper machine doesn't always translate to exact roll sizes, and you've got the problem where you're running butt rolls on the winder. In some cases, some mills are having to deal with 10 or 12-inch butt rolls, which is a very big hazard, especially if they're large diameter, and the potential for these butt rolls to fall over. That's a case where you should look at your trim removal system and determine the capacity. If it can handle wider trims, it could be upgraded to a vacuum conveying system and or an ejector system as well. But in addition to that, you'll have to look at trim chute assemblies and getting those wide enough to handle that wider trim. But that's one way of avoiding and trying to get out of the current issue of running butt rolls. Okay, real quickly, we got a couple examples to show through. We're kind of getting there on time a little bit, but winders that had safety upgrades, some of the devices that were used, you can see a new ejector, core loader, pivoting front drum splice guard that also acted as a knife. We've got some threading improvements there in the slitter section. Also, this particular winder did have tail end gluing, and also we utilized a new cradle there. This shows all of the different features. I won't go and read them all, but you can see there's considerable amount of sensing devices with all the safety fences, light safety scanners, light curtains, a fair amount of additional work other than just the actual assemblies we just showed. So this is more related to the safety improvements. If you can kind of envision an old Beloit winder in your mill, which I'm sure there are many, this is a winder from a mill in the southeast in Georgia, a couple shots prior to the safety upgrade. Probably looks familiar to many of you. This is the look at it after the rebuild, where essentially, if you remember those building blocks, the fencing, gates, and guards, and also the second one was electrical control. Those two main elements consisted, were the bulk of the rebuild here. So kind of gives you an idea of all the things you can do. This particular mill did like basically block 1 and block 2. And that gives you a little better idea graphically. Hopefully you can all see that. But all the different areas of sensing, the latching, they did do some threading improvements, the retractable gate at the unwind, to name a few, but gives you an idea of what was that rebuild consisted of. And just a couple more here. This particular mill in Florida obviously needed a safety upgrade as well. They had the need for improving the discharge. They went with a new roll barrier, hydraulic raise and lower roll barrier, a new cradle. They did some rider roll improvements, but also there's many broke holes in the mill now that are typically open, basically openings in the floor that are in some cases not protected at all. And this mill decided they needed to remove broke with a broke removal tail prep drive, and we applied the appropriate covers to today's standards for that. And here, this is another look at that same winder, but the discharge side, one real, I guess, thing to point out is typically your fencing on the discharge side of the winder will typically go all the way to your first deck stop. And there was a considerable distance from the cradle discharge to the first deck stop, what this shows here. So it was a fair amount of fencing. Obviously, you have access gates into that area, but gives you an idea of some of the other features that winder was rebuilt to. And then lastly, this shot here just gives you a view. If you've got an in-feed system coming from your reel to the winder, and you've got a number of parent reel storage positions, this is an example of a winder in the Midwest that rebuilt that entire area, all the way from the reel brake station with access control into and around that whole in-feed area, as well as the winder. So that's another area that needs to be looked at. There's obviously hazards there as those reels, jumbos, move down the rail via gravity typically, and a number of areas that need to be addressed there. So, all right, so we'll try to wrap this up and give you a couple points to kind of maybe leave this discussion with, so that when you are looking at being faced with a safety upgrade in your mill, the main point, start with a real clear idea of the level of safety that you're going to try to hit at completion. And many times, if you have a safety spec within your corporation, that gets pretty clear, and you've got a head start there. But as you move up those safety improvement steps that we discussed, obviously you're going to increase the level of safety, but you're going to also increase the cost. So the term we used before, how safe is safe enough, is really something that needs to be established at the start of your project. And then the last point, which we just were reviewing, is really you need to consider your winder and how well it currently keeps up ahead of your paper machine. And if it's tight, you really should consider some of these automatic functions to gain back that capacity, but also remove the operator from those hazards. So with that, we certainly thank you for your attention, and we are open to some questions.
Looks like we have 2 questions in the chat box. If you guys want to look in that column, one from Matthew and one from Steve.
Okay, Matthew, let's see here. So could you briefly describe a general guarding example for a small dual drum style winder with a lift table, not a cradle? Okay, well, you've got when you say lift table, I'm guessing you're referring to a bridge assembly. You still have access, if I'm thinking correctly, the access with that bridge, if it raises and lowers, still provides access to the front drum. So some of the same things we just showed in and around the front drum would apply, but I think because that lift table, being a bridge, has the ability to raise and lower, you certainly would want to latch that, provide mechanical latches, and then monitor that as well, so that you're able to ensure safe conditions before entering into the area. So that would be one thing to look at. Lee, any other thoughts there?
No, I think that's, we really have to look at every situation, and not knowing exactly what you mean here, it's a little difficult to get more specific than that.
But the second note, scanners were tried but have issues with trim ribbons tripping the interlocks. That is an issue with scanners and light curtains. Obviously, housekeeping is important. Those areas need to be kept clean to avoid intermittent trips of that. So I think if we understand your question correctly, with you're again on the lift table, not a cradle, we just need to make sure that we're able to latch that in and around that and then monitor the condition of that table. Okay, the next question was from Steve, and he's referencing an ISO 14119, section 8.4, discussing the release of guard locking device. Assume a PLD required safety circuit based on risk. The note 1 states the speed detection function is part of the SRP/CS. How does Tappi normally sense the safe condition speed of the machine or zone before unlocking of the guard door for that zone?
Yeah, we normally have safety rated speed sensing relays. These are fed primarily by tacks off of the end of the motor. If it's a rider roll or a lead-in roll that doesn't have a motor, we put sensors on there that are fed off of I guess a gear or a round disc that looks like a notched disc, and using a safety proximity switch, it feeds the safety relay, and it will count those going by the notches. So we add safety rated speed sensing relays.
I think the second part of that question maybe, it says these are high inertia rolls that can cause high, when you say high inertia means, the way I read that is maybe it's not a driven roll and it's freewheeling, so that there is no braking or controlling speed. In the example of slitter section area where you know, let's just say that guide roll and or table rolls are still rotating at a high speed to allow them in there. In those cases, we've actually added brakes, a mechanical brake to say a guide roll, or for the sake of these, let's say, low inertia slitter table rolls, which are typically aluminum and they can spin for a long time, we'll actually add surface brakes to those of some form if they're going to get back in there and thread. So that's an area, if I interpret the question correctly, if it's not a driven roll, like Lee just described, we'll have to add some form of brake and assure that that roll reaches zero speed before they can get in there. Let's keep going along. Safety respect.
Next question.
Okay, next question from Bertie.
Yep. Keep going.
Oh, okay, I'm sorry.
Keep going.
John, can operators still troubleshoot sheet imperfections with a strobe light while the winder is operating? Yes, they can, John. If they're looking at the sheet between the unwind and the slitter section, I guess maybe assuming a vertical slitter section so they can actually walk in there. That speed in which the operator can get into that interlock gate would be typically limited to around 500 feet a minute max. So we can still consider that a safe condition. Obviously not at high speed, but typically if you're going to inspect the web, I'm assuming you're looking at a slower speed maybe than that. And yes, that is possible for sure. Okay. Is the risk assessment you reference an actual audit? If not, do you have a copy of the risk assessment you reference?
We do, I'm sure us and other vendors do actual winder audits. That part of the result of that audit will be a risk assessment. If we have a complete set of drawings and perhaps photos of the winder, we can do risk assessments using drawings and photos, but we prefer to do the risk assessment as part of an audit.
Okay. That looks like that's it. Board for questions?
Mm-hmm.
Okay. All right. Any other? Okay.
All right. If anyone has any other questions, please feel free to put them in the chat box. We'll give you guys a couple more minutes to ask any last-minute questions you may have. All right. Well, thank you so much to Tom and Lee for the wonderful presentation. If you have any further questions, please contact our presenters at the emails provided on the screen. This webinar will be available in the coming weeks on tappi.org. Once you close your window, there will be a short survey. We would appreciate your feedback. We thank you for joining us today, and this concludes today's webinar.